Hello party people, let's make some noise, cause we gotta be solving algorithmic coding challenges. Going to our favorite website LeetCode.com, opening the contest section and joining the 2016 weekly contest. 4 problems to solve within an hour and a half from 3 to 6 points of difficulty. First problem, check if 2 string arrays are equivalent. Given 2 string arrays word 1 and word 2, return true if the 2 arrays represent the same string and false otherwise. A string is represented by an array if the array elements concatenated in order forms the string. Okay. I believe there was a join operator that you can apply to array of strings to join them into a single one. Let's see if my Java API memories are not tricking me. Here I am saying Java and typing Java. It's a static method on the string class. Okay. We don't really need the variables. And this one-liner should solve it. We're comparing the concatenation of the first array of strings with the concatenation of the second array of strings. But just not to be too cocky. Okay, alternative solution. I'm just looking at the requirements. Alternative solution, if we did want to do it in place and not create new string variables, would be just to go over the characters in every string member of the string arrays, one by one, and compare character by character. We could do that manually, and then we would have the method doing everything in place, not using additional memory. But it's such a simple problem. I think this way works fine. And here's the proof. We solved our first problem. Moving to our next one. Problem number 2. Smallest string with a given numeric value. The numeric value of a lowercase character is defined as its position, 1 indexed in the alphabet. So the number value of A is 1, the number value of B is 2, and so on. Number value of Z or Z is 26. The numeric value of a string consisting of lowercase characters is defined as the sum of its characters' numeric values. For example, the numeric value of ABE is equal to 1 plus 2 plus 5, 8. You are given 2 integers n and k. Return the lexicographically smallest string with length equal to n and numeric value equal to k. This is the standard lexicographical definition. You can find it online. Here's my thought on this problem. Because we have a fixed number of characters in every string, we would want to create a string with as many A's as possible. If I could put, let's make something simpler. The sum needs to be 8. So I'm gonna put as many A's as possible and then move to the next value. This would be one way to do 8. This would be another way to do 8. F is 6. And then you would have other ways to do it. A lot of ways to do it. You can do it like this, and you can do anything else really. It can start with another character. A lot of combinations to get to 8. This is a translation of this string. If you invert the requirements, having as many A's as possible means having as large as possible letters at the end of it, because the bigger letters you put at the end, the more space for A's you have in the beginning. And so what we can do is build the string from the back to the front, putting as big characters as possible, as close to the end of the alphabet, which means starting with Z's if the number is above 26, or with whatever is the closest to our number, and then try to leave room for as many A's as possible as we're approaching the beginning of our string. The number of characters left should be equal to the remainder of our target k, so that we can put only A's from there on. So if my number is 30, I'll put one 26. Okay, let's call it 33, and I had 6 characters. I would put first a 26, then I would put, what's there left to put, 4, or maybe 3. Yeah, so that would be, I'll put the maximum possible, and then a letter that would allow me to put only once after it. My target is 33, I'm putting a 26, so my target here becomes 7, I'm putting a 3, and my target here becomes 4. And my target here now is equal to the remaining positions, which means I can put just ones or A's. Okay, let's do it like this. To be hyper efficient, which we really don't need in a competition like that, I'll use a string builder just because it's the right way to build a string. I will even apply some amazing enterprise patterns and modularize my toInt method. Or I guess sure. Let's test our newly created method. It prints correctly A, and for 26 it would print Z. Cool. Let's go the other way around. Let's move down remaining characters. Do I need a special case for reaching this? I probably don't. Okay. This is the extra space I have to use outside of ace, or the slack for my numbers. So because of my constraints here, I'll always have room for an A. So for sure, I can always at least have an A, meaning I'd never run into the situation where I have a 0 to put because I've run out of characters. At the very least, I can put only AAs. So K would be at least as big as N. However, K can be way bigger than N, right? And then I'll have some so-called slack. It can be 25 extra. And then +1 for the A. It cannot be more than 25 plus 1. It cannot be more than 26 because we don't have letters that are above 26. Now I will subtract this number from K and then continue. Let's see, can I do this? Let's try 327 to understand a bit better what am I doing here. $25.00. That actually does not look correct. Oh yes, because I need to remove the current index. Get rid of this variable. Let's rename this to value. What I'm doing here, again, let's go through the logic one more time. We have a target number, 73. To be able to have as many A's in the beginning of the string, or as low characters as possible in the beginning of the string, which will make it smaller lexicographically, that means we have to have as big letters as possible at the end of the string. So these are equal conditions. The higher letters I have at the end, the more room for smaller ones I'll have in the beginning, because the sum, the total, needs to be the same. So I cannot just have A's in the average case, right? I'll need to have higher letters, and I'll want to group them at the end so that I leave space for the smaller ones in the beginning. And that's what I do. I start from the end, put as big letters as possible there, while at the same time making sure that I have enough value to put at least A's. I don't want to run out completely. I don't want to put only Z's and then have no value remaining to fill with the A's. I don't want to go over K. So obviously I need to eventually start reducing my numbers. In the solution in general would be only Z's at the end, only A's in the beginning, and somewhere in the middle you'll have a different letter potentially. You group the Z's as big as possible at the end, then you use a smaller number so that you can transition to exactly A's for the remainder of the string, of the beginning of it. And let's submit our solution. It works as expected. Okay, let's take a look at our third problem. Ways to make a fair array. You're given an integer array nums. You can choose exactly one index, 0 indexed, and remove the element. Notice that the index of the elements may change after the removal. For example, if this is our array, if we remove 1 here, which is at index 1, then we'll have 6, 7, 4, 1. And then if we remove 2 from the original array, it would be 6, 1, 4, 1. And removing 4 would just remove the suffix element. An array is fair if the sum of the odd indexed values equals the sum of the even indexed values. Return the number of indices that you could choose, such as that after the removal, nums is fair. You're being asked how many are those indices that you can remove to make the array fair. And in our example 2, 1, 6, 4, if we remove index 0, you will have 1 plus 4, which is 5, it's 0 index, so 1 and 4 at the even indices, and then 6 at the odd one, which is different. If you remove the second element, it will become fair, because 2 plus 4 would be equal to 6, and so on. And here, if you remove any of the elements, you would have fairness. At the last example, there is no removal that would make the rest of the elements matching. If I remove 2, 1 is not equal to 3, and so on. And we have 10 to the 5th elements, 10 to the 4th size of a single element, only positive numbers. Let's think about this together. Ooh, thinking. A removal of an index would change all indices after that removed element from even to odd and from odd to even. In other words, all the elements before the index of the removed one would stay as they are in the original array, and the rest after would swap. I'm thinking some prefix sums maybe of the even and the odd elements taken separately can be used to immediately calculate in constant time for every index whether after removing that element the sums of evens and odds would be equal, would tie. Here is what I imagine. Let's add a few more elements just for the sake of example. So the moment I remove this 6 here, every element after the removed one would shift one position to the left. This is what's that? Even, odd, even, odd, even. And my 5 is odd. 5 would become even. This thing that was even would become odd, and so on. Every element after the removed one would switch from even to odd and vice versa. And so if I have a pre-calculated sum and I know what's the sum of those elements that are at even or odd positions, I'll be able to, after the removal, immediately recalculate my sum. I'm taking what's on the left, which has not changed, and then I'm taking what's on the right, which has changed. Let's see. 2, I want to have an extra element. Oh, of course that was not correct. I should have done it by even and odd elements, but let's first just check if my perfect sums calculation is working as expected. Zero, 2, 3, 9, 13, and so on, 38. Looks good to me. Let's do it carefully using odd and even numbers separately. 2, 8, 14, 18. And then the others are 1, 5, 10, 20. Okay, so that's all correct. I have the prefix sums split by even and odd numbers, having those separately. If you notice here, at even positions you have the even prefix sums, and at odd positions you have the odd prefix sums. I'm calling these even because it's 0 indexed, so 0, 2, 4 and so on, and this is 1, 3. Okay, and so now if I remove this here, which is index 4, 0, 1, 2, 3, 4, before that I'll have 5 and 8, and after that I'll have 18 minus 14, which is 4, and the other would be 20 minus 5, which would be 15. Let's go again over those and accumulate the correct answer. If int even equals to prefix sums I minus 2. Let's call it first or second because it can be even or it can be odd, depending on whether we are at an even or at an odd element. So first part you will get prefix sum, second you will get prefix sums I minus 1. And we are removing the current element, that won't be counted. Next, if first is less than, yeah, I guess I'll need to know whether we're at an even or at an odd position. I'm wondering, could I simplify this by adding a couple extra elements on the back as well, the way I've done it on the front, so that I don't have as many checks. And I can do that. If index even, if n is even, then my last even would be n minus 1, I guess. Or because we have this extra 2 elements, it would be like that. And then last odd. Last even is 20. And then remove this print. Add 2. Okay, that's correct. And then if my number is even, okay, I'll have to think a bit more about those checks. The edge cases are really tricky to my slowly operating brain at this point. I'm leaving. Let's drink some water. H2O. That's a powerful booster. I want to make sure that there are elements after my current one, so I do the correct subtraction. Let's try the original idea. That would be my calculation. Now I don't need to worry about indices. I added some filler values. Here one more equals to this one. Here one more equal to this one, so that the difference between them is 0. I'll still be iterating from 2 to 20 here. Otherwise, from index 2 to index n plus 1. And I'll add n plus 2 and n plus 3 indices, so that I can have more generic logic. We'll have first plus last. If we're at an even number, we need to add the odd ones to the first. Actually, what we just did here would be good. And then add the even numbers to the second number. Else, we'll do the other way around. Second, first. If first equal to second, answer should be incremented. Let's simplify our array just a bit. Minus the current one. Okay. And if it was even, let's take a look at 2. Okay, that looks correct. Three. And in the case of 1, 2, 3, I should get a 0. Alright. What we did here is we're keeping prefix sums separately of the even and the odd numbers. And then when we're removing an element at an index, all of the numbers to the right of it shift, which makes it so that you need to add the sum of those numbers to the opposite number. So if they were even, you gotta move them as odd and add them to the odd numbers from your first part of the array, and vice versa. And that's good. That's absolutely correct. Let's look at our last problem. Minimum initial energy to finish tasks. Let's see how much time we have left for it. 27 minutes. You are given an array tasks where tasks I is equal to actual I and minimum I. Actual I is the actual amount of energy you spend to finish the ith task. Minimum I is the minimum amount of energy you require to begin the ith task. For example, if the task is 10-12, if your current energy is 11, you cannot start this task. However, if your current energy is 13, you can complete this task and your energy will be 3 after finishing it. You can finish the tasks in any order you like. Return the minimum initial amount of energy you will need to finish all the tasks. Okay. You will have actual energy, which is always lower or equal to the minimum energy. And so the requirement to start a task would always be higher than the actual energy spent on completing that task. And so in this case, you start with 8 energy. When you finish the first task, you will be left with 7 energy, which is enough to start the second task. At the end of it, you will be left with 5 energy. And boom, you won't be able to start this task. I guess that's why they show you here in the example, you need to start with the task with the highest requirement. And the requirement is 8. You finish the task, you spend 4 energy. Then you start the next task, you're left with 2 energy, and then you start the first task. And we would have an extra energy left at the end of it, but we cannot start with less than 8 energy because then we would not be able to ever start the last task. Okay, several things here. First, there are 2 things to optimize against, it seems to me. One is we have to have enough energy to start. So we want to start with the tasks that require most energy. At the same time, we want to also go first through tasks that deplete or use minimum actual energy so that we have more to complete the requirements of the future tasks. I'm thinking, can we do a binary search in the space of the required energy? I can try with 1000 energy and see if I can complete the tasks, or I guess at the minimum of the integer space. If that works, then I'll try with half of that and so on until I find the minimum energy. That looks like it may be possible. However, I still need the proper sequence of executing tasks. I'll have to go through tasks in some order. From one point of view, I need at least 7 energy, because this is the sum of my first elements, and then the maximum of my second elements is 8, so I also know that I'll need at least 8 energy. How to know if I'll need more than that, as in this example here? What if I maximize the difference between required and spent? Great, they gave us quite the examples here. Let's write some examples. It seems to me if I sort them by difference in energy, it may work for me. Let's see if that's true. And at the very least, at the end, I'll need leftover energy that's equal to the last gap, the smallest difference at the end, plus whatever is the sum of all actual energies. Sum of actual energies plus last gap. Okay, maybe let's do this. Let's first sort by gap. A1 minus A0 minus B1 sort them in the correct order. I want to start with the biggest gap, right? So let's do this. This would be a method, because if they have equal gaps, I'd want to start from what? From the largest element. Let's order them as a secondary property by the largest first. The minimum answer would be the sum of our actual. The minimum answer would be the sum of all actual numbers plus the difference in the last one, or you can think of it all actual numbers except for the last one, which would be the required energy. Let's take this number of tasks as a separate variable. And then let's make sure this is not less than the biggest requirement. $27. And in this example, 32. And this example probably will be 8. However, now I'm almost 100% convinced this is not the correct answer. But hey, I'll try, right? Probably this will be wrong. Just immediately to construct an example. And then what I'm thinking now is I can actually go binary search from this upwards until I find a number that solves my problem. Oh. Huh. But what do you know? Huh. And that's it. I guess it was easier than I thought. One more time, what I did here was I sorted them by difference, which I really didn't need to do. I could have just taken the, I guess just the minimum difference, and that would be enough. Let's write this in a bit of a prettier way. Total actual plus min diff or max required. Oh yeah. Okay, so the solution is really look at the all actual effort required, add to it instead of the actual, the required for the last element with the minimal difference, or I guess you can just calculate like I do the minimal difference and add it to the total actual requirement. Then also look at the maximum required energy for any element, and that was that. Let's take a look at where I am. Pretty far back. I guess it was an easy round. Well, I'm happy. Let's think about this again. So you could say that, oh, forget it. Oh, shucks. We're done. I'm glad we did that together, guys and girls and everyone else. Stay positive, stay focused, keep coding, excel, prevail, get the dream jobs, get the best total compensation or whatever motivates you to get your dream job. Maybe get the best family because you have the best job and the best wife would marry you to give birth to your best children, or the best husband will marry you to give birth to work on you getting into the situation to give birth. Hey, whatever, guys, let's get the positive messages and see you in the next weekly contest. See you when you're ready to tackle together some new challenges. Hasta la vista, amigos.
If you know what I mean. Wait, what?
Hello, friends. It is with great sadness that I must share with you that, as I suspected all along, the solution of the last problem was incorrect. Specifically, question number 1665, minimum initial energy to finish tasks. If you notice, this solution here, very fast, well, it's just not correct. And why is it not correct? Because it's linear, it doesn't take advantage of the fact that you need to go and execute tasks in diminishing size of their difference between minimum and actual energy. So if we test with this test case, it doesn't go through. There is a working solution, just as I was thinking, but never went to implement it because the incorrect one passed. The correct solution, one of the possible solutions, is to sort the tasks like so, in decreasing gap between actual and minimum in every tuple, and then to binary search for the correct answer. So you sort them, and then you start looking for energy between 0 and integer max value. Or you can find a better lower bound, but that's fine. And as you search on every iteration, you check, is the energy that I've just chosen enough? And if it is, then I will go down. And if it isn't, then I will go up. And eventually you will converge on the correct minimum energy required. There is an even better solution. And that solution you can find in the discussion section of this problem. Let's look for consistency at the Java solution. The way to solve it more efficiently is to sort and then in linear order go down and try to execute task after task. The moment you find you don't have enough energy for the current task, enough minimum energy, then you need to add energy. Imagine you're paying out of pocket, and every time you don't have enough money, you keep adding from your pocket until a pile out of your pocket adds up. This pile, added to the original amount you had, is what the answer is. Take a look at the discussion section to find the best n log n solution. My, again, n log n binary search solution is a bit slower than this. It still works though, it solves the problem, not as fast as the hacky incorrect solution, but still pretty decent, faster than 37% of the solutions submitted. Let's do one more thing and see which companies gave that problem. This was asked by Akuna Capital. If we go and check out the other problems from the contest, we will find out. One was asked by Dunzo, ways to make a fair array. I have no idea what Dunzo. Another was asked by Lending Cart, and Facebook asked the easy one. Hey! Anyways, this is to come and prove we should be checking our solutions and not be too excited when something seems to work. Trust your gut feeling. See you next time. Bye.